Hi everyone. Today we are going to have a look at the second way of analyze the loading in members of a truss. So today we're going to look at a section analysis as opposed to the joint analysis of last time. So the key difference here is, once again, we have the same problem. We want to find the forces in members BG, FG, and FE. So this time, instead of isolating a particular joint and then work out how the members attached to that joint are loaded, this time instead we're just gonna take a section of the structure and use that to figure out the loads inside each member. Now, once again, we're going to use the same principle that if the whole structure is in equilibrium, if all of this, then regardless of how we divide this thing up, every part of it will also have to be in equilibrium. So once again, if the whole thing is in equilibrium, any part of it is in equilibrium as well. So it will take some experience to figure out, but in this case, the easiest cut to make is here, because this single cut will include all three forces we're trying to figure out, all three members, and without introducing extra unknown members. Sorry, unknown forces. So if we make the cut here, then what we end up with is basically this. Sorry, it should be cut. Yeah. Yeah. So the forces here will be the 270, and the force here will be 300. And this will be BG. This will be FG, and this will be AF, and then FE. So we're trying to find out the forces in these three members. So as you can see here, this single cut includes all three unknown forces, and but it doesn't really contain any more. So it's usually want to minimize the number of extra forces in your sections to simplify the calculations. Okay, so now the whole thing is equilibrium, which means it doesn't spin around, it doesn't move up or down, or left or right. So the thing is, let's try to figure out what BG is first. Yeah. Okay. If we try to use the vertical forces, the forces in the vertical direction, there is none. Yeah. So BG is entirely horizontal. So we want to check what's the horizontal, but then we have two unknowns, which means it cannot be used to help us to directly find out what BG, the force in BG, is, because we actually have two unknowns in the horizontal direction. Now, one quick way to figure out how what BG is doing is extended the whole thing slightly. So let's use a different color. Yeah. So if you look at this point, let's call it P here. Can you see that if we take moment about P as a point of reference, then can you see that 300 force downwards is trying to rotate it counterclockwise. 270 is trying to turn it clockwise. And the BG, what BG is doing, I say it's turning the whole thing counterclockwise, because 270 times this distance is like, it should be, the distance here is doubling the distance here. So 270 here is has an arm, the force arm that's double the arm of this 300. So this will create a much larger moment than the 300 force to turn it clockwise, which means for the whole thing to stay equilibrium, for the whole thing to not rotate around P, BG has to act go towards the left. So acting, producing a counterclockwise moment. So that's what we can figure out. Of course, what is the length here? If each individual member is 1 meter, then obviously this is the angle here is 60 degrees, isn't it? So the height here should be sine 60, isn't it? 1 times sine 60. So we have an arm of sine 60 degree meters, and if we tally up all the moments, so 270 times 1. Yep, so that's 270 times this one, creating this goes clockwise, has to equal to 300 times 0.5. Okay, so like if you assume the direction of BG wrong, it doesn't matter, you just get a negative answer in the end. So you will know that the direction is opposite to your assumed if it's not as obvious as in this case. 300 times 0.5 going counterclockwise, plus BG times sine 60. Yeah. So the moment going clockwise about P has to be counteracted by these two moments going counterclockwise. Yeah. So what makes that? So it makes BG sine 60 equals to, what's that? So 270 times, minus 150. So it's 120, and BG equals to 120 divided by sine 60, which means the force in BG is approximately 138.56 newtons. Yeah. So we have BG, so it just turns the whole thing, turn the whole thing counterclockwise. And of course, because it's pushing against the joint, so it's a compressive force, because it's pushing against it. Okay, now so that's it. We have BG now. Okay, now let's look at FG, because FG is actually a simple one, because you have a 270 Newton going up, 300 Newtons going down. That means the vertical part of FG has to, plus the 270 going up, has to cancel out the 300, isn't it? So that means FG, because it's 60 degrees, so FG sine 60, so that's the vertical part. And then the horizontal part should be this one, so FG cosine 60, yeah? If all the forces, vertical forces, as you can see, Fe and Bg have no vertical component. Only vertical force here, the unknown vertical force is here. So if all the forces in the y direction has to be 0, that means 270 plus Fg, the vertical component of Fg, has to equal to 300. Yep, 300 coming down, 270 going up. So Fg sine 60 equals to 30, and then Fg is approximately, so what's 30 divided by sine 60? It's about 34.64 newtons. Yep. So that's the simplest one. Now, generally speaking, you want to make sure that there's minimum amount of unknown forces in one particular direction. So if we made the cut somewhere else on the truss structure, we may have more than one vertical unknown forces, which would have made things slightly more difficult for ourselves. But here we made the cut. We made sure that there's only one vertical unknown force. And then finally, we want to find out what Fe is. Yeah. So Fe, as you can see, is a horizontal force. Yeah. Conveniently, what we have is horizontal force in BG, horizontal component, and that's the only horizontal forces, and they should be in equilibrium, which means okay, so sorry, by the way, this is compression. It's because as you can see the direction of these forces. So it's a compression again. So BG is going this way to the left. The horizontal component of FG is going to the left as well, which means for the whole thing to stay in equilibrium, Fe has to go to the right to counteract it more. Yeah. So that means if the forces in the horizontal direction have to be in equilibrium, then Fe has to equal to Bg plus the horizontal component of Fg. So cosine 60, which means Fe is just 138.56 plus 34.64 times cosine 60, which means Fe is approximately, if you add all of them together, they should be 155.88 newtons. Now, in terms of the direction, as you can see, Fe has to go in the direction indicated, has to go to the right, which means it's pulling away from the joint and making it a tensile force. Yeah. And that's it. So this is how you use section. You probably would need some more practice on identifying the best places to make your cuts. But this is like how it works. And so there is that.